Welcome to the demo of Klepsydra's Earth observation solution based on CAN-Open protocol. Modern spacecraft onboard computing solutions usually involve a cluster of small computers interconnected via CAN bus. In this demo, we will present a distributed solution that involves two interconnected computers. Computer 1 connected to the camera. It will capture images and send them via CAN bus. And Computer 2 connected to the Earth data link. It will receive the images from Computer 1 for Earth download. Our design is quite simple, from bottom up. One CAN-Open plugin that works as a normal middleware connector, our data transmission protocol that allows sending large datasets over CAN bus, the main application services, which are camera capture and Earth data link download. The technical setup is the following. The computer is a Zinc 7000 board. The operating system is Petal Linux. Use of BusyWait to increase throughput of images, simulated camera, and Earth data link. One of the key features of Klepsydra is that it uses no external dependencies. Therefore, it is simply a matter of copying the software to the computer and running it. At Klepsydra, we differentiate between application code, which is the implementation of the desired functionality. Typically, it is split into small testable units or microservices, and composition code, which wires the microservices, middleware, and configuration together. We will look now at the composition code. The main blocks are configuration, monitoring setup, event loop, and middleware setup. Notice that with just 3 lines of code, we have created the core high-performance internal engine. The application services, setup, scheduling, and shutting down. The client and server code have a similar structure. The processes are already running in the Zinc boards. Let's go to the monitoring visualization tool. Klepsydra uses NASA's OpenMCT for monitoring the performance of the system. First, we look at the system monitoring where we can see the CPU and RAM consumption. We have here both the total usage and the application's usage. One of the features of Klepsydra Running Time Engine is that all the required memory is pre-allocated at startup time. As you can see in the graphics, the process RAM usage is completely flat. This is very important for 2 reasons. First, it increases stability and predictability, as nothing is left for the operating system to optimize. Secondly, it substantially increases performance as no time is spent in allocating or freeing memory. Both client and server are using BusyWait. However, the CPU usage is quite low for the server. The client CPU usage is larger as it is actively polling the bus for new images at almost 1 kHz. Let's go now to the most important part of the demo, the performance analysis of the application. We first go to the client publication monitoring. There are 4 charts. Top left is the publication rate. It can be seen that the polling, the blue line, is running at the configured 950 Hz. The middle lines are the publication to CAN bus, which is by nature more unpredictable. Top right is the average publication time. As with the publication rate, most publishers are extremely fast, Only the can open publishers are more time-consuming. Bottom left, we have the number of discarded events, that is, the events that could not be published on time. Finally, bottom right, we have the event allocations. This is the memory management done by Klepsydra. It can be seen that with the exception of strings, no memory allocations are performed. The server publication statistics are quite similar to the client ones. We go now to the client subscription monitoring. We have 4 charts. Top left is subscription rate. Similar to the publication statistics, the client copes very well with the high frequency polling. The middle lines are the subscriptions to CAN bus data. Top left is the subscription average time. It can be seen that most subscribers are quite fast in processing the events. Only the CAN bus internal queue takes more processing time. Bottom left, this is a very important feature of our software, the time that an event stays within Klepsydra's pipes before being delivered to the application. The high performance of our software here is clear. Finally, bottom right, we have the discarded events, which are the events that could not be processed in time and had to be removed. In this case, not one event was discarded. The server subscription statistics are quite similar to the client ones. With this setup, we reached a throughput of 150 to 200 kilobytes per second. Now that we have seen Klepsydra Earth observation in action, let's have a look at further improvements. One of the key elements in any satellite application is the capability to shut down non-critical processes, for example, when the battery is low or the temperature is high. This can be easily done in Klepsydra. As we are in a CAN open environment, let's assume that there is one battery sensor and one temperature sensor, both connected to the network. We can poll these sensors via the standard object dictionary of the CAN open protocol. Based on these values, we can build some logic, like a simple hysteresis loop. The control service class shows a simple implementation of the capability to shut down. We can see that the constructor receives a system publisher, which will control the Earth observation services, and a CAN open callback handler, which we will use to communicate with the CAN bus. Then we have the execution method. This method is invoked by the scheduler. We poll both sensors using the callback handler. 2 main design patterns can be seen here that we use extensively in Klepsydra: the builder pattern to build complex structures, and lambda functions to hook listeners to events. This kind of programming style makes the code very expressive and simple to maintain. Finally, we have the function that performs the hysteresis loop to control whether the Earth observation services should run or not. In this demo, we have seen the Earth observation solution that Klepsydra offers for distributed computing in satellites. We have shown that our solution is not only very efficient in performance and stability, but is also a framework that is extremely easy to program with. Thank you and goodbye.